Welcome back, and in this lecture we're going to talk about the most difficult module on the board, and that's the ADC module. We only have one of them, and ADC stands for Analog to Digital Conversion. Essentially, your pick is a voltmeter. It can measure voltages. You've already seen it measure voltages with the button. It could tell if the button was pressed or high voltage or off low voltage. We're going to proceed and see how it's much better than that. Now, there's two ways to use a voltmeter. One way is to take your voltmeter and, as we usually do it, measure it across a resistor. Okay? Then, according to Ohm's law, the value you get from the voltmeter is equal to the current flowing through these resistors times the resistance R4. The way ADC voltages are calculated, it's as if you always connect one leg of the voltmeter to ground. We often did that in some of our calculations when we wanted to check the voltage. So now the number here is not 1.27 because it's measured with respect to ground. If I measured the voltage from here to here, right, then I could work these all out. Right, so if I measure the voltage from here to here, it would be 3.86 minus 1.27. There are 10 pins on your pick that support ADC operations. They're labeled as AN0 to AN5, AN9 to AN12. Let's go down to the next page where I've got the pin out diagram, and in blue I've highlighted the pin numbers. So these are the analog input numbers. You'll see for 2 and 3 I've put X's in front of them. Our pick is programmed using these 2 pins, and sometimes the ADC can screw up the programming, so we don't do that. So stay away from AN2 and AN3. In purple, you see that AN0 is also a pin called VREF plus and VREF minus. We'll tell you about those a little later. So we've got this odd numbering because this is a small 28-pin chip. The standard pick has 44 pins, and it would have 13 AN or analog input pins. AN0 and AN1 may be used to provide reference voltages, what are called VREF minus and VREF plus, for ADC. In that case, they can't be used for ADC. Now, digital input-output, when we use that, was only 1 bit. It could read a high voltage or a low voltage. Our ADC is said to be 10-bit. Means that it can read 2 to the 10 values. If you get your calculator out, 2 to the 10 is 1024, but we start counting from 0. So the possible values of ADC are 0 to 1023. So the ADC module, when it measures a voltage, doesn't return a voltage number. It just returns a number between 0 and 1023. And it's your job to translate that into a voltage. So, what value between 0 and 1023, for instance, would be the same as 1.125 volts? We're going to have to figure that out. If the ADC module returns a value of 632, what voltage has it measured? Those are the basic things that we need to work on. Now, to get to figuring out those answers to those questions, we have to know something about voltages. Typically, voltages are smooth and continuous. Something like this ramp here. On the other hand, if I'm trying to measure the voltage here, and I've only got 10 to the 24 numbers to represent it, then essentially I'm replacing the ramp by a set of stairs. So the ADC values are which step you'd be on. If a voltage falls in a bin N, assign N as the ADC measurement value. Okay. Remember, on the stairs you can only be on a step. You can't be right here on the stairs. So this range of voltage would be on this step. Okay, so how big are the bins? Well, that's fairly easy. If you go back here, we know the bottom is typically 0, and the top is, for most of the time, we're going to use 3.3. And we have 10 to the 24 bins. So that means each of the bins is 0.003223 volts wide. So then, suppose we have a voltage that's 2.74 volts. What's the number of the step or bin that it would be on? Well, you take that voltage and you divide it by the bin size, okay? And you will get a number, in this case 705.6, but you can't have 0.6 of a step, so it rounds down to 705. Be very clear here, even if it was 35.999, it doesn't round to 36, it would always round down to 35. Okay, so what range of voltages actually lie in that step or bin 705? So 0 is 0 to 1 bin size, and then from 1 bin size to twice that. And if you go down to bin B, well, the lower end is the bin times the bin size, up to B plus 1 times the bin size. So in our case, bin 705 is actually a range of voltages from 2.2720 volts to 2.2752 volts. Now we ordinarily don't know the input voltage, right? You use a voltmeter to measure voltages you don't know. So instead of coming back with a range of values, what we usually do is say that if you're in a bin like this, say bin 705, then the possible ranges are from 2.2720 up to 2.2752. We'll draw something like an error bars between those two and give the central or average value. So bin 705 we'd say would be in the middle, which is 2.2736 plus or minus 0.0016 volts. This is the formula. Bin size plus a half, so the middle of the bin, times the bin size, and then the range is plus or minus half the bin size. That's the size of the error bars. Just what you do when you plot graphs in the physics lab. Okay, now here are the actual formulas outlined in purple here. These are the formulas we use, and these formulas, notice they say Vref plus and Vref minus, and there's this extra term Vref minus here as well. So these two formulas are the general formulas for doing your calculations, and the ones that you keep on hand when you're doing ADC. Now, why Vref and V minus are in there and not VDD and VSS is in the ADC module, you can actually say, instead of using VDD, use a smaller voltage, Vref plus, and instead of VSS, use something that's a little bigger. So the references are closer together. The number of steps still is 1024, but now the steps have shrunk. They're a little bit smaller, so we get more precision. And precision in physics is always the goal. So those formulas have Vref in them, and they correct for the fact that the lower end, the Vref minus, isn't 0. Okay? So ADC only reports from 0 to 1023. What if the voltage was down here between Vref minus and VSS? ADC doesn't have negative numbers. It's going to give you the lowest number possible, which is 0. It's going to read 0 for any voltage below 0. Similarly, if any of the voltage are above your reference voltage, it can't go any higher than 1023, so it reports 1023. If we're using these reference pins, then AN0 and AN1 can't be used to sample because we're using them for our fixed references. Here are a couple of examples of what would happen if you were using a different reference voltages. On the left-hand side, we're using the regular references, VDD and Vref minus. That also means we have 2 extra pins that we can use to collect data. So the questions are, what's V if B was 127? And if V was 2 volts, what would ADC report back for the value of B? So we just pull down the 2 formulas we have. And here, if B is 127, we always take the middle of the bin times the bin size plus the reference, right? But the reference is 0. So that gives us 0.4109 volts. Plus or minus the bin size, which is 0.0016. Similarly, for 2 volts, subtract off the Vref minus, which is 0, so no change, and divide by the bin size. We always have to round down, so B will be 620. On the right-hand side, we've changed Vref to be 2.5 and Vref minus to be 1.0. We're using the same values of B and the same input voltage. We want to see how they change. So in this formula, it's still 127.5, but the bin size is smaller. We're using a narrower range. But we have to correct for the new minimum, which is 1.0. So the voltage now is 1.1868. The bin size, because it's smaller, this result for the voltage is more precise. See the difference between these two. Okay? So you always need to know what the reference voltages are. Similarly, if the voltage is 2, what will B be? So 2 minus 1 times the bin size, okay? Or divided by the bin size, I should say, and works out to 682. So the results are quite different. Okay, so we've talked a little about the formula for the conversion and using these references, but we haven't talked about the electronics. And now we're going to talk a little about the internal electronics and algorithms that ADC uses. So there's 3 elements. To do ADC, you need a constant signal voltage. But if you're using a voltmeter, your signal could be changing, so we've got to talk about that a bit. You need a piece of electronics called an comparator, which just comes from the word compare, so it's a piece of electronics that compares 2 voltages. If you're comparing a voltage, you need something to compare it to. And the simplest thing to use is what's called a voltage divider. Now, when you're comparing, you want to compare efficiently, so you're going to use some sort of algorithm. The method that it uses is, and is usually shown, is the method of successive approximation, or the high-low game. You'll know this game, right? Somebody will say, I'm thinking of a number between 1 in 100, what's the number I'm thinking of? And you'll get to guess it. So you'll say, is it greater than 50? And they'll say yes. And then you'll say greater than 75, and they'll say no. So now you know it's between 50 and 75. And so usually you subdivide the intervals you're talking about. That's the algorithm we're going to talk about. Okay, but before that, right, input voltages are usually, or certainly can be, varying. They don't always have to be, but they can be varying. And the thing about ADC, all the stuff we need to do, compare voltages, and take time to do. And that time, over that time, the voltage could change. So you can't do ADC with varying voltage signals because you can't accurately do a comparison. Are you comparing the voltage down here or the voltage up here? Imagine playing the high-low game with somebody who keeps changing their target voltage. That would be extremely annoying. Okay, so ADC needs a constant voltage to compare with. You need a way to quickly capture a voltage from a changing signal, is what that means, because ADC doesn't capture it fast enough. What we use is something called a sample and hold circuit. It uses a capacitor and a resistor to very quickly sample the voltage. It doesn't measure it, it just holds the voltage, and it's a constant voltage then that we can compare to. So we quickly capture the signal voltage, do ADC on the captured voltage, then you capture the next voltage, do ADC on that, capture the next voltage, do ADC on that. Okay, so the sample and hold circuit is shown down here. These are 2 points measuring an incoming voltage, which I'm trying to show as a varying voltage. And the circuit depends on a resistor and a capacitor. The time to fully charge this capacitor depends on R times C, something called the time constant. In about 5 RC, 10 RC, that capacitor will be fully charged. So if you close the switch, then very quickly this capacitor charges up. Then you open the switch, and now the capacitor is fully charged, and there's a voltage over it. This works in reverse. If you have a charged capacitor and a resistor, you can discharge it really quickly. And flashes on cameras use these RC circuits to hold a charge. You use a battery, which is kind of slow in supplying current, charge up the capacitor, and then you drive all the energy of the capacitor in a very short time through the flash. Nice big flash. Okay, so here's TADC. It's a long time, but the sample and hold is much faster, and so we're getting some voltage in here, and that'll be good enough, right? So there will be a little uncertainty about the voltage, but you're not too concerned about that. It's far better than if we were trying to do ADC on this signal. Okay, here's the electronic symbol for a comparator. You've got 2 inputs, a V1 and a V2, and it asks the question, is V1 less than or equal to V2? Right? Yes or no. So, like all things in electronics, it's digital. It's either no or yes, 0 or 1, low or high. Okay, now to do the comparisons, you need other voltages that you know. So here I've got what's called a voltage divider. It's just a long series of equivalent resistors. I've got 8 of them here. Okay. And if you do Ohm's law on these guys, if this is plugged into ground and this is plugged into power, so 0 to 3.3, then the voltage at these different points are just fractions of the difference between the top and the bottom. It's easy to work out using Ohm's law, so we won't bother to do that. And so here's your comparator. Here's the input signal from the sample and hold circuit, and you're going to compare it to these different guys. Now this is known with 8 resistors. 8 resistors is 2 to the 3 resistors. This would be 3-bit ADC. Remember, we've got 10-bit ADC, so 10 to the 24, right? So I wouldn't be able to draw that here. So this switch S moves about, and the more resistors in the voltage divider, the smaller the range or bin that the voltage could be found in, right? So that's why you want numbers like 2 to the 10, 2 to the 12. Here are the bins that you would find, right? The bin numbers and the bin sizes. Okay. Let's look at the algorithm. So just like the high-low game, you start in the middle, right? And you ask the question, is the input greater than this voltage or less than this voltage? Right? If it was yes, you move to the in-between again, right? So if you started here and it was higher, then you'd move here, right? And you'd say, is it higher than V6 or is it less than V6? Right? And again, you would switch, and let's say yes, then you would move to here, and then is it bigger than V7 or less than V7? So you're answering 3 questions. You get 3 bits of information. Okay? So this would be a binary number. So if it was no, 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 you'd be down in bin 1. If it was yes, 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 like the version I just did, you would be in the top bin. Right? You'd be in this range. Okay? So we've got all of these things. So let's try this for V equals 2.25. Okay? Right? Is 2.25 bigger than this? Yes. Is it bigger than this? Yes. Is it bigger than this? No. So it would be yes, yes, no. We'd be in this bin. Okay? And that would be, the ADC would report back 6. Okay. Now if you want higher precision, right, you'd require generally more bits, which takes more comparisons, and each comparison takes time. So the more comparisons you do, the more time you need. So in ADC, you have a trade-off between the precision you want and the speed, and internal electronics too, but generally talk about the trade-off between precision and speed. Okay. The next item we want to talk about is the ADC buffer. When you make, didn't mean to do that. When you are using ADC and doing the calculations are held in memory, okay? And that memory is not permanent. Okay? So our pick, you can do it with a single pin or using all 10 pins that we have on ours. But we only have one ADC module. When you do ADC on multiple pins, they're done sequentially. So you measure the voltage on pin 1, then you measure the voltage on pin 2, then you measure the voltage on pin 3. And then when you're finished, you go back to pin 1 and do the next measurement. Okay? And so on and so on. So to hold the results, it goes into a piece of memory called a buffer. And buffer is just a general term for something that holds a number, but not permanently. Our buffer has room for 16 integers. It can also be split up into 2 8 integer buffers, and we'll explain why we would want to do that. So if you wanted ADC to use 5 pins, the measurements go into the first 5 buffer positions. During the ADC conversions, a buffer holds the intermediate answers to the yes-no questions. When the ADC has completed, the buffer holds the value of B. So if you read the buffer before ADC is completed, you're not going to get the right value for the voltage. Okay? If you're calling ADC more than once, right, the next time you call it, the positions and the previous values of the conversions are overwritten. You have to put the result into permanent memory before that happens. Okay? It's like you're doing long calculation on your calculator, and you got one big calculation to do, and then another big calculation, and then you want to add the results. Somewhere you've got to write down the number from the first calculation so that you can add the second one, unless you've got a fancier calculator. To let you know when you can safely start to read the buffer, so when it's completed and the value in there is the correct voltage B, and so that you can save your temporary data from being overwritten, ADC module has something called a flag. So when it finishes, pardon me, a conversion, this flag is set, right? So a flag is just a 1-bit portion of memory. A set flag memory bit is just 1. When it's cleared, its value is 0. The user, your job is to clear it once you've read the number. Okay, I'm going to try and explain the buffer to you now. It's not super complicated, but we want to step through it slowly. First of all, let's assume we're asking for ADC to be done on a set of 3 pins. We'll call them AN4, 5, and 9. There's 2 modes we can use. We're going to set the ADC to manual or automatic modes. In manual mode, ADC measurements start or occur when we tell them to. In automatic mode, they just happen continuously until the module gets turned off. Okay, so let's imagine we're in the manual mode. We say collect a voltage. So at t equals 0, my 16 integer buffer has nothing in it. After one ADC, the first measurement is in the first position in the buffer. After the next ADC, okay, we've got our second measurement. Third ADC, we've got the third measurement. Here's the flag, right? Because you told it to measure 3, the flag goes on when you've finished all 3. Okay. Here it is in the automatic mode, okay? The 16 integer buffer, right? Every multiple of ADC, it fills up. There's a flag, so you better read it now. But by the next time it's entered, you've overwritten, right? This is the second reading. You've overwritten this guy, then this guy gets overwritten, this guy gets overwritten. That flag warning, you've got to be watching for like a hawk, right? And you don't get a lot of time. You only get 1 TADC, which is actually a very short time, right, to get. So using the automatic mode with a 16 integer buffer, that's not great. What you normally do is you split the buffer into two 8 integer buffers called A and B. And so now when you do the automatic, when ADC, first one goes into A, second goes into A, the third goes into A, here's a flag goes, oh, so you know we've filled the data. And then down here, the next one, it starts filling the second buffer. So you've got more time to read these three numbers, right, because these are in somewhere else. The last one, now they're overwriting again. So by splitting the alternating buffer, you get more time to read. And in particular, if you're trying to do lots of different things, this is less likely for you to miss a number, miss a reading. So if we use the automatic measuring, we're always going to split the alternating buffer. Okay, main points about the buffer. In manual mode, choose the 16 wide buffer. After the flag sets, read at your leisure. You're the one, or at least before you try to do ADC again. You clear the flag before you call ADC again, right? Right, if you don't clear the flag is still set, so you might try and read it at the wrong time. In the automatic mode, choose the split buffer and alternate between filling the two buffers. In the auto mode, must immediately save buffer. Again, you must make sure that you're right on top of saving the results to permanent memory. Okay? If you don't do it, it gets overwritten. So you must be very careful about that. Just want to talk a moment about what happens if your sampling rate is too low. Here is something, is a sine wave, right? If I measure the signal too slowly, then when I plot my values, it looks like I've got a constant signal. Okay? So your sampling rate has to be faster than the frequency of the signal you're getting, roughly about twice to 5 times faster, to get enough points in here so that you could actually reproduce something like a sine wave.